Hi dear students, this is Bhavsab Sononi, Assistant Professor, Department of Chemistry, Local Education Society's Arts, Commerce and Science College, Jawar, District Palghar. Dear friends, in the last part of the video, we started the discussion on molecular spectroscopy, and in the previous lecture, we particularly discussed about the concept of dipole moment and how this dipole moment is useful in order to predict the correct structure of the different types of the molecules. Dear friends, in this part of the video, we are going to talk about the polarization of the molecule which leads to the dipole moment, because dipole moment is very important in the study of spectroscopy, molecular spectroscopy. So how this dipole moment is produced in the molecule, that we are going to discuss in this part of the video. So here, very generally, we all are well known about any molecule is made up of the two types of the composition. One is the central nucleus and another is the electrons. So here it is observed that whenever these molecules are placed in an electrostatic field or in electric field, then this field is responsible for the distortion of electronic structure and also responsible changes of the equilibrium position of the nucleus, which gives rise to the separation between the center of positive and the negative charges. The displacement of electron is called as electron polarization in presence of electric field, and the distortion of nuclear charge is called as atomic polarization. So distortion of electronic charge in the nucleus in the presence of an electric field is called as electron polarization, while the distortion of nuclear charge is called as atomic polarization, and the sum of these two, that is electron polarization and the atomic polarization, the sum of these two is simply called as distortion polarization, or it is also called as induced polarization. So this electric field is responsible for this induced polarization, which leads to the dipole moment in the molecule, and the dipole moment is called as induced dipole moment, and this induced dipole moment is the product of polarizability of molecule and the strength of the applied electric field indicated by means of capital E. Here you can see the figure. Here this is the molecule in absence of electric field, and this is the neutral molecule, but in presence of electric field there is separation between positive and the negative charges, leads to the formation of two poles. One is the partial delta charge, another one is partial delta negative charge, and that leads to the dipole moment, and this molecule is called as the induced dipole moment. So this polarizability is the measure of ease with which the molecule can be polarized, and distortion or induced polarization per mole is simply called as molar induced polarization, and it is related to the alpha. This molar induced polarization is related to alpha by the equation 4 by 3 pi n into alpha. N is Avogadro's number, alpha is the polarizability, and p pi is the constant. So this non-polar molecule acquire dipole moment whenever kept in presence of electric field. This effect is temporary and it disappears as soon as the electric field is removed. And these polar molecules in absence of electric field are oriented in all possible directions due to thermal effect. But when such molecule is kept in presence of electric field, then they get oriented so that its positive end is near negative pole, and the negative end is near to positive pole. This is called as orientation polarization. That leads to the orientation polarization in the molecule, and hence the total molar polarization is the sum of induced polarization or distortion polarization and orientation polarization. And this distortion polarization is the sum of electron polarization and atomic polarization plus orientation polarization in case of a polar molecule. And definitely this dipole moment is very important in the study of rotational spectra of the rotating molecule. And actually the presence of dipole moment, it is the prerequisite condition, it is the required condition for the molecule to undergo rotational motion and to show the rotational spectra. This microspectroscopy is found to be very useful in the determination of structure of those molecules which do not give a good result by means of IR or Raman spectra. So those molecules which do not give good results by IR or Raman spectra, that molecule gives a very good results with microspectroscopy, which is also called like the rotational spectroscopy. The source of micro radiation is klystron tube, and it is electronic oscillator in which the beam of electron is pulsed between the cathode and the reflector. As a result, monochromatic radiations of about 95,000 megahertz are produced on molecular level. So only here, this is very important, only those molecules can absorb micro radiation which have resultant dipole moment. This is the essential condition for the molecule to absorb micro radiation and to show the rotational spectrum. So only those molecules will absorb the micro radiation which have resultant dipole moment. Means only those molecules will show rotational spectroscopy or the microspectroscopy which have resultant dipole moment. Such molecule on rotation generate electric field, and definitely this electric field is capable to interact with the electric component of the micro radiation, and that leads to the rotational energy changes in the rotational energy level, and the microwave spectrum is observed. So here this can be explained with the help of rigid rotor. Rigid rotor is simply the something in which the 2 point masses are joined by a bond or the equilibrium distance. Here this is not important, but this is the two rigid masses m1 and m1. These are joined by means of some bond distances, and this rigid rotor is having moment of inertia. So how can we calculate the moment of inertia of a simple rigid diatomic molecule? That can be discussed here. So for that purpose, we are going to discuss the rigid diatomic polar molecule having mass m1 and m2. Mass m1 and m2, these are the two atoms of the rigid diatomic molecules, that is, which are joined together by means of a simply internuclear distance small r. So m1 and m2, these are the atoms, rigid atoms, which are separated by the internuclear distance r. And r1 and r2, these are distances of these atoms from the center of gravity or the center of mass about which the molecule rotate, and hence the moment of inertia of a particle m, any particle having mass m, is revolving around the fixed point at a distance r, then its the moment of inertia is always given by mr square. This is the concept in the physics. So here we have this system, rigid atomic molecule. Here the mass atom having mass m1, another atom having mass m2. These are joined by means of internuclear distance r, and r1 is the distance between the center of mass or the center of gravity and the atom 1, and r2 is the distance of separation between, or distance between the center of mass or the center of gravity and the another mass another atom having mass m2. So this is the rigid, and these two masses, this is the diatomic molecule, is revolving, is rotating around the center of mass or the center of gravity. So for the atomic molecule, the total moment of inertia is given by I is equal to m1 r1 square plus m2 r2 square, and as the system is balanced, the moment of both the atoms are equal, means m1 r1 is equal to m2 r2. So from this equation we can write the equation for r1. This is not the r2 square, remember this is the r1 and this is only the r2, not r2 square. So r1 is equal to m2 r2 divided by m1, and r2 is equal to m1 r1 divided by m2. And if we put these values, so from equation 1.6, this m1 r1 square plus m2 r2 square, if we put these equations in this equation, then we will get I is equal to m1 r1 into r1. This is the splitting of this r1, written as the r1 into r1, plus r2 square is written as m2 into r2 into r2. And if we put the values of r1 and r2 from the equation 1.1.6 1.1.7, then we will get this equation m1 r1 into m2 r divided by m1, it should be m1 plus m2 r2 divided into m1 r1 divided by m2. This m1 and m1 will get cancelled, this again m2 get will cancel, and we will have this equation I is equal to m2 r1 r2 into r1 plus m1 into r1 r2. If we get this r1 and r2 as a constant, as a common term, then in the bracket there will be m1 plus m2. So finally we will get this equation, and as you know, total distance of separation between m1 and m2, it is the sum of r1 and r2. And from this equation, if we will put the value of r2 from this equation, and this, then r1 plus m1 r1 divided by m2, we can take the r1 common here in the bracket, a1 plus m1 divided by m2. After the cross multiplication, it will become m2 plus m1 divided by m2. So you can write this as a m1 plus m2 divided by m2. And if we can write this equation for r1 from this equation, so r1 into m2 divided by m1 plus m2 into r1. So this is the equation for r1. Similarly, if we will put here the value of what, r1, then we will get the equation for r2. And similarly from this equation, that we will have equation for r2 as m1 divided by m1 plus m2 into r. So this is very simple. Okay, and if we put these values of r1 and r2 in equation 1.1.9 here, if we put the equation r1 and r2 here, if we put the equations of r1 is this and r2 is this, if we put these two values here, then this m1 plus m2 will get cancelled, and there will be only one at the denominator. That we will get the equation I is equal to m1 m2 divided by m1 plus m2 into r2 square, and this term in the bracket m1 plus m1 m2 divided by m1 plus m2 is known as the reduced mass, and it is indicated by mu. So this final equation for the moment of inertia of rigid diatomic molecule, rotating molecule, is I is equal to mu into r square, and this is very useful equation for the calculation of moment of inertia of simple diatomic molecule, where the internuclear distance is r and respective mass of the two atoms are known. So from this we are also able to calculate the energy of the rotating molecule, and here the energy of rotating molecule can be also calculated with the help of Bohr's quantization of energy. If a molecule is rotating with angular velocity omega, then the angular momentum is always integral multiple of h upon 2 pi. If the molecule is rotating with angular velocity, then the angular momentum is integral multiple of h upon 2 pi. Integral multiple means it is in the multiple of n. So this angular momentum of this molecule, rotating molecule, is nh upon 2 pi, and the angular momentum of body rotating with the angular velocity omega and having moment of inertia is given by I into omega. So this is also the angular momentum of a body rotating with angular velocity omega and having moment of inertia. So both are these angular momentum. So we can equate these two by means of this equation, nh upon 2 pi is equal to I into omega. So as the quantum conditions are applicable to the rotational system, so angular momentum should be jh upon 2 pi and not the nh upon 2 pi. So we will replace this n by means of nj, and we will get the equation this jh upon 2 pi is equal to I into omega. So this j is called as the rotational quantum number, having the values from 0 to onward, 0, 1, 2, 3 like this. And the kinetic energy of the rotating molecule is simply given by means of an E of rotating molecule, energy of rotating molecule 1 by 2 into I into omega square. So on multiplying and dividing this equation by means of an I, we will get E of rotational is equal to 1 upon 2 I into I square into omega square. As we have the equation for I into omega j into h upon 2 pi, so we can write the equation for I square into omega square is equal to j square into a square upon 4 pi square. And if we put this equation in this equation, so definitely we will get the equation for energy of rotating molecule, as E of rotating molecule is equal to J square into A square upon 8 pi square into I, and on applying Schrodinger wave equation to this equation and quantum restrictions to rotational energy, it gives the equation E of rotating molecule is equal to H upon 8 pi square into I into J plus 1. So this is the equation for the rotational energy of rotating molecule, or rotational energy levels of the rotating molecule, as H square upon 8 pi square into I into J plus 1. So this is a simple equation, and definitely from this equation we are able to determine the energy of any rotational energy level of the rotating molecule with the help of different values of J, which is called as the rotational quantum number of the rotating molecules. So this is very simple. So from this we are also able to calculate the frequency of the rotational lines and the energy of different rotational line also, and we will be able to compare the energy difference between the different successive rotational energy level in the rotating molecule. So dear friends, we will resume again in the next part of the video to discuss about the frequency and the energy of rotational energy levels or the rotational lines and the separation of energy difference between these lines. So thank you very much. We will resume again in the next part of the video.